Today's talk is about alcohols, phenols, and ethers. We're introducing a new element, oxygen, to our molecules. So let's introduce what an alcohol is. So these contain an oxygen, whereas our alkenes and alkynes and alkanes did not before. And this oxygen, in the simplest case here, is going to make two bonds. It's going to have two lone pairs, much like it does in water. And instead of attaching it to yet another hydrogen, as we have in water, we're going to have this bond on the one side or the other be attached to a carbon chain. So it's a carbon chain represented by R here. And then instead of fully saturated with hydrogens, one of the hydrogens is replaced with an OH. Okay, it isn't an entity called an OH. It's two atoms. It's an O bonded to an H. So when you connect them, you must connect the oxygen to the carbon chain and the hydrogen on the other side. This still has the bent geometry, right? Electronic geometry, still tetrahedral because of the two lone pairs. But instead of an H here, we have an OH attached. Now we can classify alcohols into three groups: primary, secondary, and tertiary. The primary alcohols are the ones in which the carbon to which the OH is attached is bonded to one other carbon. Okay? Secondary, accordingly, the carbon to which the OH is attached, so locate the OH first, and I'm discussing the carbon to which it is attached, has two other carbons bound to it. And then finally, tertiary is the carbon to which the OH is attached is bonded to three other carbons. Now, we did this before when we were classifying carbons as primary, secondary, tertiary, quaternary, with pretty much the same rules, except you can't have quaternary alcohols. And the reason for that is this carbon can't make 5 bonds. Right? If you tried to make a quaternary alcohol, the OH would be on a carbon bonded to 4 other carbons. But that would mean that carbon has 5 total bonds, and that's not possible. So one of its bonds must be to the OH, and that leaves me at most 3 others. So primary, secondary, or tertiary. The primary ones, there is one situation where the carbon to which the OH is attached is bonded to no other carbons, right? And that's the case of methanol. So methanol truly isn't fitting the definition of primary, but as we'll see, it behaves like primary alcohols. It reacts like primary alcohols. It has all the properties of primary alcohols. So what we'll do is group methanol, since it's sort of unique, into the rest of the primary alcohols. Okay, so primary bonded to 1, or in the case of methanol, none. In the case of secondary, it's bonded to 2 other carbons. And in the case of tertiary, this carbon is bonded to 3 other carbons. Okay, so some basic rules. I'm not going to ask you to learn the common names. We're not interested too much in those in this class. But let's go over the IUPAC rules, the more systematic naming system, naming method. So we're going to apply what we've done before, the longest possible chain, longest continuous carbon chain, except now on your list of priorities, wherever it is on your back of your notebook. So at the very bottom, you wrote hydrogen. Above that, you wrote everything else. And then above that, you should have triple bonds. And at the top of your list currently is double bonds. Right above double bonds, and we're going to keep adding to the top of this list, right above double bonds, write alcohols, right, where we have our hydroxy groups. So this is the highest priority thing on your list. So as far as your IUPAC naming rules, I want the longest continuous carbon chain. Now it can't include the alcohol because it's an O, it's not a carbon. But I must include the carbon that the OH is attached to. Right? Much like we were doing back here. I was identifying the carbon as primary, secondary, or tertiary. It's the carbon of interest, the one the OH is on. That's the one that must be in the main chain. Right? It doesn't have to be at number 1, but it must be in the main chain. The next step is to number that chain such that that carbon, the one the OH is on, gets our lowest number possible. Okay? When it's in a ring, that's by default number 1. We've seen that before. But if it's in a straight chain, you can number in one of 2 directions. So we're going to number such that the carbon the OH is on gets the lowest possible number. All the other substituents get what they get, right? If you don't win the race, there's no trophy for second place. The others just get wherever the numbers fall, okay? And to make sure that we understand this is an alcohol, we change our ending, much like we did with the other ones. We drop the E, right, the final E, so a propane would become propanol, right? We lose the E and we add OL. right? And I'm purposely saying it as propanol. I'm emphasizing the last syllable there. So you hear it in my voice, it's an all, not an ow or an eel or anything like that, right? So propanol, if you had the all ending. Okay, let's look at a few simple examples and then we get more complex ones to teach you how to do it. The absolute simplest one would be methanol, right? So let's find the longest continuous carbon chain here. Of course, it's the only carbon present that contains the carbon on which the OH is placed, which there's just one carbon. That's as simple as it gets. So we call it methane, then change the ending from E to OL, so methane becomes methanol. There are no substituents here. That's the simplest as it gets. Okay. Underneath it is ethanol, right? So this one is a 2-carbon chain, right? The longest carbon chain possible would be both carbons. I must include this carbon in the chain. Not a tough act to follow here. And then which of these 2 carbons would be labeled number 1? Well, it would be the one the OH is attached to that gives it the lower number. If I start counting here, this would get 1, 2, and the OH would be on carbon 1. If I start counting here, 1, 2, the OH would be on carbon 2. That's a poor choice. So I'm going to choose to give the carbon the lower number possible. So this is 1, this is 2, ethanol, ethane becomes ethanol, and no substituents. In the middle picture at the screen, middle row, top segment of the screen, there are 3 carbons in this chain, right? The longest possible chain is 3 carbons, and it must include this one. It doesn't necessarily have to start at this one, but it must include it. And to get the longest one possible would be all 3. Counting from right to left, it'd be 1, 2, 3, and this carbon would get assigned 1. And from left to right, it would be 1, 2, 3, and the OH would be on 3. Well, that's a poor choice again. I want the lowest number possible, so this will get 1, 2, 3. So what would you name this? We have 1, 2, 3 carbons, so propane. Let's change the ending from E to OL, so it becomes propanol, but that's not enough information. Unlike the first 2, no matter how I look at it, the OH was on number 1, no matter where it was placed. Here, if this OH were attached in the center, it would be on carbon 2. So it's not necessarily always on carbon 1. Here, no matter where you put the OH, either side, it would be carbon 1, and here there's only 1 carbon. So I need to indicate where the OH is. So in front of the name propanol, I'm going to affix a 1. Right? So it'll be a 1-propanol, as opposed to the one right below it, which would be the 2-propanol. So 1, 2, 3 carbons again, but the OH, again, this carbon had to be in the main chain, so it's still 3 long, propanol, but it's on carbon 2 this time. Since both of these options exist, I need those numbers to give them unique names. Here, the 2 on the right, the one at the top, we need to find the longest continuous carbon chain that includes this carbon, the one the OH is attached to. So that would be 1, 2, 3, 4. 1, 2, 3. That's not the longest one. So 1, 2, 3, 4. 1, 2, 3, 4. No matter how I do it, the longest I'll get is 4, including this carbon. So now my options are to make this end the low number or this end the low number. So I'm going to go with the lower number for the carbon on the OH. So I'll choose this one as 1, 2, 3, 4. I could have gone to here as 4. I could have started here as 1. But as long as you get 4, giving this one the lower number. So 1, 2, 3, 4. So I included this one. I have some substituents that are not accounted for in that name. So 1, 2, 3, 4 would be called a butane. I changed the ending to all, so butanol. Don't call it butol. You've lost a syllable if you do that. So butanol. Where's the OH? It's on 2. Do I need the 2? Yes, it could have been on number 1. It could have been sticking off the end like these others. So it's a 2-butanol, and it's got a couple methyl groups. Where are the methyls? They're on 2 and 3. Right? So 1, 2, 3, 4. On 2 and 3, we have methyls. So this would be called 2,3-dimethyl 2-butanol. And then the last one at the bottom, with the ring, I need to include this carbon, the one to which the OH is attached, in the main chain. This line between the carbon and the oxygen is just a bond. There is no carbon here. The carbon's at the intersection of the lines, and this end does not have a carbon. It's attached to an O. If this OH were not here, then that would be a methyl group, if it just had a line sticking out. But it's actually going to a bond, right? Just like over here, this bond, this line sticking up from this carbon does not indicate there's another carbon up here because there's an H written there. Right? So there is no carbon in this line. Right? So the longest continuous chain must include this carbon, the one to which the O is attached. And since it's a part of a ring, then we must include the ring as the main chain. You're either in the ring or you're not. You can't be both. So the ring becomes the main chain. So a 4-carbon ring would be called butane. We add the prefix cyclo to indicate that it's in a ring. So cyclobutane. And then of course it's got an OH. So we change the ending from E to all. It becomes cyclobutanol. Where is it? Well, it's on the first carbon because I can make the beginning anywhere I want. But I don't need the 1 in the name because by definition, no matter where I put it, it'll be number 1 in a ring. Right? So this was just called cyclobutanol. I don't need the 1 to locate it. Right? Here's some more examples. They're a little more complex, but you apply the same rules. So this one on the top, find the longest continuous carbon chain that must include this carbon. Right? Doesn't mean I start here. I must include it. So if we start, let's say here, 1, 2, 3, 4, 5, 6. If I start out here, 1, 2, 3, that's not long enough. So 1, 2, 3, 4, 5, 6. The longest chain I'm going to get is 6. So I would name it hexane. Right? No double bonds or rings or anything. So hexane, change the ending. Hexanol, where is it located? It's on number 2. If I start counting from this end, it gets number 5. That's too long. So it's a 2-hexanol. And then what's on it? I've got a pair of methyl groups. And they're on 2, 3, 4, and 5. Right? So 2 and 5. So I'd get a 2,5-dimethyl 2-hexanol. Okay, so the 2 and 5 describe where the methyl groups are. And the 2 describes where the alcohol group is on the hexane. Right? It's perfectly valid to put this 2 in between the hexan and the all if you want. You can plop it in there. That's a more modern way to do it. Sometimes you have to do it that way. But for this case, or the more traditional way to do it, is keep this word together, hexanol, and put the locator in front of it to tell me where the OL or the OH group is. Okay, the one on the right, we have the longest chain must include this carbon. Do not count this line as a carbon, and do not count this O as a carbon, because it's an oxygen, it's not a carbon. So I can start here as 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5. So it's 5 as the longest chain. So it's going to be a pentane. I changed the ending, pentanol. Where is it? It's on number 1. So it's a 1-pentanol. Do I need the 1? Sure, this OH could have been attached, say, here at 2. So it's 1-pentanol. And then it has a methyl group down here on number 1, 2, 3, 4. So it's a 4-methyl 1-pentanol. Okay, and the last one at the bottom, we have a ring structure. So the OH is attached at this carbon. So this carbon must be in the main chain. Now, if I can't start it out here, go around the ring, and then go into the other methyl groups. You can't go in and out of rings. So you must be either in the ring or you're not. So this OH is attached to a member of the ring, so we're going to count the ring as the main chain. So it's a 1, 2, 3, 4, 5-membered ring. So a cyclopentane. Change the ending, cyclopentanol. It's by default on number 1, so I don't have to tell you that. Right? But it has 2 methyl substituents. Where are the methyls? Well, this must be number 1. I can't start counting here and give them 1 and 3. This must be number 1. I can choose to go around the ring either way, but no matter how I do it, these are going to get numbers 2 and 5. Right? Or if I start here at 1, this would get 2 and 5. Right? So either way, I'm going to get a 2,5-dimethyl, right, cyclopentanol. And I don't need to locate where this is on the ring because by default it's on number 1. It gave it its name. Okay. Looking back at these, I have one other question. Could any of these possibly have cis or trans options? What's the requirements for cis or trans? I either need a double bond with differences on each side, and we talked about that in the previous lecture, or I need a ring with exactly 2 substituents not on the same carbon. Well, no double bond, no double bond, no ring, no ring. The top 2 cannot. The bottom one has no double bonds, but there is a ring. Well, does it meet our criteria? Does this ring have exactly 2 substituents? Well, you might think initially, yes, I see 2 methyl groups. But when I say substituent, in terms of naming it, yes, there are 2 substituents, 2 methyl groups I needed to include in the name. But this ring is wearing 3 things. So when you're talking about cis or trans options, I mean, does the ring have 3 attachments? When I say substituents that way. So yes, there are 3 things. So this does not qualify for cis or trans. I need exactly 2 things on the ring, not 3. When you're naming it, yes, we're calling these methyl group substituents, not really calling this a substituent because it gave it part of its name. Right, so be careful how you discuss it, because if you say it has 2 substituents, I agree if you're talking about the name. If you're talking about whether it can be cis or trans or not, I count all 3 things on the ring, and 3 is more than 2, so it doesn't qualify. Okay. What if you have more than 1 hydroxy group? Right? We did this when we did methyls earlier. We called them dimethyl and such. So what if you have 2 OH groups? So treat it the same. Find the longest continuous carbon chain that must include, if possible, both of those carbons, because these are on different carbons. Right? So we must include both of these in the main chain if possible. It's entirely possible, so we'll try to get both of them in. And in this case, it is the only pair of carbons there, right? So it's just 2 carbons long. This is not 1, 2, 3, 4, 5 carbons long, or 1, 2, 3, 4, or 1, 2, 3. It's 1, 2. Lines are not atoms. Right? So 2 carbons long, what do we call it? Let's start with ethane. Right? But there's an OH group, so we should change the ending. It becomes ethanol. But there are 2 of them. We generally indicate 2 by using the prefix di, but I'm not going to call this diethanol because there aren't 2 ethanes there. I want to put the di in front of the thing I have 2 of. So I'm going to put the di in front of the all. I have 2 of those. So instead of saying ethane or ethanol, we're going to say ethane diol. We leave the E to make it pronounceable in English, because otherwise we'd have 2 consonants next to each other. So we just leave the E on the end. So ethane diol. Where are they? Well, they're located on number 1 and number 2. Do I need to tell you that? Yes, because they both could have been on number 1. It could have been a 1,1 ethane diol. This one's in fact a 1,2 ethane diol. We could have also had a propane diol. This one has 3 carbons. Same scenario, just 1, 2, 3 carbons long. And the OH groups are on 1 and 2. So it's again propane diol. There's 2 of these things, and here's where they're located. We could have the same propane with an OH on each one. 1, 2, 3. Right? So 1, 2, 3, propane triol, because there's 3 of them. And because it says tri, I'm going to need 3 addresses. Could these be anywhere else? Certainly. I could have put all 3 on one end. It could have been a 1,1,1 propane triol. It could have been a 1,1,2 or a 1,1,3. There's lots of options, so the numbers are necessary. Okay. Some other examples with alcohols and their least favorite word, isomer. All of these, if they're isomers, have to have something in common. And that means they have the same formula, right? The same inventory of parts. So they all have the same number of oxygens, they all have the same number of carbons, they all have the same number of beryllium atoms. Happens to be 0, but it's still the same number. Right? So in the first case, how do you assure that all 3 of these are actually isomers of each other? Well, let's figure out their formulas, but we're going to do it an easy way. The first thing to do is count carbons. Right? Just literally count them. So this has 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Yes, they all have 5 carbons. And in fact, if you checked all of these, they all have 5 carbons. The next easiest thing to check is oxygens. 1, 1, and 1. They all have 1. Okay? The more difficult thing to check is hydrogens, and I don't want to count them, because then I'd have to draw them. I don't want to count them at all. I'm going to use math. These might seem easier to actually draw and count, because there's be 3 here, and 2 there, and 2 there. You're likely to make a mistake somewhere. And even if you don't, it takes longer to count them by drawing and counting than it is to do math. Especially if I give you a problem that says there's 80 carbons in this alcohol. How many hydrogens does it have? You do not want to draw it. It may take the entire exam for you to draw it correctly. So instead, let's use some math to figure it out very quickly. So it has 5 carbons. How many sites of unsaturation does it have? Well, no rings, no double bonds, no triple bonds, none, no sites of unsaturation. So it follows the basic formula, CnH, 2n plus 2. The fact that there's another H on the end of this O does not mean you add another hydrogen to the formula. The oxygens do not change the formula. What it's really saying is instead of this H that would be sticking off this carbon, there's an OH. There's still an H there. So the number of H's has not been altered by the addition of this oxygen. So follow the formula, CnH, 2n plus 2. And that's the case for every one of these, right? So 5 carbons, there'll be a total of 2n plus 2, 2 times 5 plus 2, or 12 hydrogens. If you want to draw one out to confirm that, you can, but it takes longer to draw them than it does to do the math. So they're all isomers of each other, but they need unique names. So let's try to name each of these. So these 3 up top, all the carbons are connected exactly the same, right? 1, 2, 3, 4, 5 in a row. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. The oxygens are placed, or the OHs, are placed in different positions. This one's on number 1. This one's on number 2. This one's on number 3. Why can't I draw a 4th one over here with it on number 4? Because then I would be counting from the wrong end. Then if I put this one on right here, it'd look just like this, just turned around. It'd be on number 2. And just like I can't put the OH on this one and call it number 5, that would be number 1 again. So you can only have so many isomers without repeating yourself. So each of these must have a unique name. 5 carbons in a row. They're all pentanes. OH, change the ending to pentanol. And then the position of the OH is either on 1, 2, or 3. So it's 1, 2, or 3 pentanol. The ones at the bottom are also isomers of this, but they don't have 5 in a row. The carbons are quite different down here. This one at most has 1, 2, 3, 4 in a row, right? And then I have a methyl group. This one has 1, 2, 3, 4 in a row with a methyl group. This one also 1, 2, 3, 4 in a row. However you want to count it, it's still 4 in a row with a methyl group. So these look very similar. So what's the difference? The first one has 1, 2, 3, 4 in a row. The hydroxy, or the OH, is on 1, and the methyl's on 2. This one gives it its name, so it's going to be a 1, 2, 3, 4. A butane, change the ending to butanol. Put this on number 1, so a 1-butanol with a methyl on 2. So 2-methyl, 1-butanol. This one is 1, 2, 3, 4. OH is on 2, so it's still a 2-butanol, but the methyl is not over here on 2 anymore, or sorry, isn't on, the OH isn't on 1, it's on 2 now. So this was 1, 2, 3, 4, OH on 1, methyl on 2. 1, 2, 3, 4, OH and methyl both on 2. And then finally, for this one, we have 1, 2, 3, 4, the OH on 2, methyl on 3. So methyl on 3, it seems odd. I should start counting from this end. Wrong. I always give the priority thing the lowest number. This carbon has priority over this methyl group. Where the OH is attached, that's our highest priority thing, is how you're going to get the lower number. So 1, 2, 3, 4, hydroxy on 2, so 2-butanol with a 3-methyl. Okay, so either 2-methyl, 1-butanol, 2-methyl, 2-butanol, or 3-methyl, 2-butanol. All isomers of each other, but they're all unique molecules. The last one down here, I have 1, 2, 3 carbons in a row, or 1, 2, 3, or 1, 2, 3. I cannot count 1, 2, 3 because that does not include this one. I must include that one in my main chain. So 1, 2, 3, propanol. The OH is on 1, so 1 propanol. And there's a pair of methyl groups on number 2. And some people will tell you this name is 2,2-dimethyl-1-propanol. There's nothing wrong with that name. It's just got pieces of information that are redundant or unnecessary. Where else could these methyls be? Right? If you try to put them on 1 or 3 of a 3-carbon chain, it'll make the chain longer. So the only place the methyls could possibly be on a 3-carbon chain are on number 2. So the 2's become unnecessary. Some people still like to see them, but I'm a minimalist, as I said. If I'm a follower of rule of leaving off unnecessary numbers, I'll do it all the time. Okay. Some reactions that we talked about previously, just briefly, and I mentioned oxidation and reduction, but let's go over what they mean. In simplest terms, for what I want you to understand, when you do oxidation, You can think of it as increasing the number of bonds between carbon and oxygen, or decreasing the number of bonds between carbon and hydrogen, or both. Okay, so let's look at an example for oxidation. We're going to use methanol. It's one of our molecules we said we're going to consider to be a primary alcohol, right? Even though it doesn't have any other carbons attached, but we'll consider it in the primary group because it behaves like it, much like our ethanol does down here. It's also a primary alcohol. This carbon only has one other carbon attached. So let's look at these two examples. If I oxidize them using this enzyme, which we'll talk about later, called alcohol dehydrogenase, it's an enzyme in your liver, right? But it oxidizes it. I'm increasing the number of bonds between C and O, one bond here, two bonds now, and decreasing the number of bonds between C and H. This carbon has how many hydrogens attached? 1, 2, 3. This H is not on the carbon. And this one also only has 1 or 2. And if I look at the result, this one goes from 3 to only 2 hydrogens. This one went from 2 to only 1 hydrogen attached. These three over here didn't do anything. They were just along for the ride. But if you do have this case where you have a primary alcohol, you can oxidize it to an aldehyde, like we just said. In addition, you can oxidize it one more time to something we call a carboxylic acid, right? And we'll talk about these later, but you notice the same pattern holds. The number of bonds between C and O went from 1 to 2 to 3. Where did this other O come from? It comes from water. We'll talk about that later too, right? But the number of bonds to H decreased. It went from 3 to 2 to 1. And with this other one down here, the number of bonds between C and O went from 1 to 2 to 3. And the number of bonds between this carbon and hydrogen, we're ignoring this one on the left because it doesn't change at all, right? So this one has 2 H's, 1 H, none. Right? So the number of bonds between C and O goes up with oxidation, makes sense, that's where it gets its name. And the number of bonds between C and O go down, right, as you go this way, so it reduces. Not quite where it gets its name, but close enough. Right, so if you remember, going to the right, oxidation, we're increasing bonds to O and decreasing the number of bonds to H. If you're doing reduction, that's going from the right side back to the left, you're going to increase the number of bonds to H and decrease the number of bonds to O between the carbon. Okay, and we'll talk about this more in our next lecture as well. Okay, but let's focus on these two primary alcohols one more time, methanol and ethanol. And they're alcohols, right? They're very, very small molecules. They only have a couple carbons or one carbon. And they have some properties that water doesn't have, right? They have different boiling points. So we can take these molecules, and if they're mixed with water, we can separate them from the water. This is called distillation, where you use a difference in boiling point of two molecules, and you can separate one from the other. Okay, so if you have a mixture of alcohol and water, in this case we're using ethanol, right, and mix them into a flask here. And if you start heating this flask, the boiling point of the ethanol is a little lower than the boiling point of the water. And it seems like it would be the other way around because water is a much smaller molecule, but water has very, very extensive hydrogen bonding, much more than any other alcohol. So it boils at a higher boiling point. So the boiling point of the ethanol is in the 70s or 75, 76 to 78 degrees, depending on the pressure. And the boiling point of the water is somewhere around 100 degrees Celsius, again, depending on the pressure. But if you heat this container, right, and you start heating it, nothing happens, right? And then you get all the way to 75 to 78 degrees Celsius, the ethanol that's in here will start to boil, right? And as it boils, it'll fall back into the solution as it cools off, right, condenses back. But some of those vapors will make their way into this glass tube on the right. So this is a gas, right? The ethanol is a gas at this point. Makes its way into this container on the right, and we have a water jacket around it, right? It's a tube inside of another glass tube, think of it that way. And we put some water in the outer chamber, cold water, and it comes out the top, so anything inside will be cooled. So as these hot vapors make their way over here, they will start to bounce off the walls of this glass, cool down, you give their heat up to the outer container, right? And then they'll condense into liquid droplets. And of course, gravity will pull them down here into a new container. So if I keep this temperature constant, right, it'll remove almost all of the ethanol. And the ethanol I get over here will be somewhere around 90 to 95% pure, because some water molecules do make their way over. right? You can do this in a controlled setting in a laboratory with these glass containers like this with a Bunsen burner and beakers and such. Or some people do this in the middle of nowhere in the woods in North Carolina. This is how they distill moonshine, right? Or it could be done under legal licensing and in factories where this little flask isn't so little anymore and it's a huge thing that contains thousands of gallons. But they pretty much do the same chemistry. You want to boil it so that the ethanol distills over and the water does not. And what if you get your result over here, this ethanol, I said it was somewhere around 90% pure or 95% pure or something like that. Some water will come over. I can take this very pure sample, right, clean the glassware out, put it in a new piece of glassware or the cleaned one, and repeat the process. Right? Now it'll get even purer. Right? The most you're going to get, however, no matter how many times you do it, unless you put some kind of drying agent to remove the water, is around 95 to 97% pure ethanol. So if you see containers of ethanol being sold, and they call it, or even alcoholic beverages, they do this too, and they call it double distilled or triple distilled or something like that to make it sound cool, it's telling you what they did. They had a solution of water, ethanol, and who knows what else was in it, right? Some yeast cells and everything else that came from the process. And we just distill the ethanol over. And they may take it and distill it a second time or a third. And that's what the double or triple distillation process is. Right? But if you heat it up too hot, and you get over the boiling point of water, then water will start to come over as well. Right? Here, the ethanol's already been removed, and we put a new bucket under here to collect the water. But if you get this too hot during this stage, you're back where you started. You didn't get rid of any water. Another alcohol you're probably familiar with is called isopropanol. Technically, the IUPAC name for it would be a 2-propanol. Here's a picture of it on the top right. Right? And this is what we call rubbing alcohol. I'm sure you're familiar with the smell. Right? It has a very unique smell. The medicinal odor of hospitals and doctors' offices is what we usually associate with isopropanol or 2-propanol. And the most effective disinfectant or infection-preventing wipe of isopropanol is somewhere in the order of 50 to 70% isopropanol. Any less than that, it's not as effective, and any more than that, it's not as effective. So somewhere around 70% isopropanol makes a great rubbing alcohol, a cleansing agent. Right? So pure alcohol, not so great, and just pure water, not as great. But about a 70% isopropanol makes the best antiseptic to clean surfaces. Right? And we do that to prevent infections. As you're going to inject someone with a needle, you're going to make a hole in the skin. Some of those surface contaminants, bacteria, fungal spores, whatever might be on the surface of the skin, if you just poke a hole in the skin, will be dragged below the surface, even with a very sharp needle. So you kind of prevent the amount of material that could get underneath by cleaning it with this isopropanol solution first. Okay? It also is an alcohol. It has a very low, or not very low, but relatively low boiling point compared to water again, and it evaporates rather readily. So isopropanol or 2-propanol evaporates very rapidly, and when it does, it cools off the skin that remains behind. Evaporation is a cooling process, so you can use isopropanol wipes to dramatically cool the surface of a patient. Okay? It's also found in delivery mechanisms of cosmetics, aftershave, hand lotions, and such because of that evaporation. Not so much to cool you off, except maybe the aftershave part, but to apply the other things that are suspended in this solution of alcohol. And then after you apply them, the alcohol or alcohol-water mixture evaporates, leaving behind the powder or the lotion or whatever was there. Right? So it's just a delivery mechanism for these things. And of course, it evaporates away. Okay? And I mentioned this before about having multiple OHs on a molecule. You can ignore these names here. These are the common names, but I wanted to show them to you, so you may have heard of them before. But this one was called 1,2-ethane diol, and this one's 1,2-propane diol. Right, so these are our molecules that we're going to term glycols. A glycol is not a name of a molecule. It's a family of molecules. Right? An example is if I gave everyone in the class something to write with, right? A pen, a pencil, a crayon, a lipstick, a knife and a chisel, and you carve it into the wood or whatever. They're all writing instruments. You could use them as writing instruments, right? But if I just call something a writing instrument, no picture comes to mind. You have to think of an example of one, right? So that's kind of what glycols are. They're not a particular group of molecules based on their structure or based on their property or something like that. It's based on having one feature, right? Like the writing instrument. It could be used as a writing instrument, right? You pretty much put anything in that category if you can scratch something with it, right? But that's what a glycol is. It's a means of describing a family of molecules, and they must possess one quality, right? So the one quality here is that there's at least a pair of OHs on adjacent carbons. Adjacent meaning next to each other, right? So ethylene glycol, or in this case the 1,2-ethane diol, is the prototypical example of that, right? There are only two H's, there are only two OHs, only two carbons, and there's one on each. They're definitely on adjacent carbons. So this qualifies. This is a glycol. The one below it is also a glycol. I don't have to have an OH on every carbon, but it must have one on adjacent carbons, right? So 1,2-propane diol qualifies. 1,3-propane diol would not be a glycol because the OHs would not be on adjacent carbons. I'll give you another example. If you had an 8-carbon chain, right, an octane, and I put OHs on numbers 1 and 2, that would be a glycol because they're on adjacent carbons. But if I had an 8-carbon chain and I put OHs on 1 and 4, it would not be a glycol because they're not next to each other. If I had an 8-carbon chain and I put OHs on 2, 3, and 5, that's still a glycol because at least a pair of them, the 2 and the 3, are adjacent to each other. They don't all have to be, as long as that scenario happens somewhere in the molecule. It's a writing instrument, right? So as long as you can use it somehow to write, you can call it a writing instrument. Doesn't matter what it's made of. Same thing here. And a little story here with these paraglycols on the left and why they're called ethylene glycol and propylene glycol. Those are common names, and they're what you see written on the back of your antifreeze bottles. So these are antifreeze molecules, right? We use them in solutions of what we call antifreeze, right? Things you put in your car or refrigerants or whatever it might be, right? And the old style antifreeze, which they don't make anymore, is this top molecule, right? And what happens is this molecule, over time, if it gets inside of an organism, somebody drinks it or an animal drinks it, or just exposed to oxygen for a long time, liver enzymes will convert it into its oxidized form. So both of these are primary carbons, primary alcohols. So both sides get oxidized once to an aldehyde, twice to a carboxylic acid, and it looks like this thing on the right. We'll talk about these more later. I'm just telling you the story behind the glycols. So this is called oxalic acid, and it's very toxic, right? It's very toxic to your liver, and if an animal drinks enough of this ethylene glycol antifreeze, this will kill that animal. Why would they drink such a thing? Well, ethylene glycol here, or the 1,2-ethane diol, has a slightly sweet taste to it, right? Don't go testing this on your own. It's toxic, but someone tested it at some point and let us know. So animals tend to drink this. So if you have an old style antifreeze in your car, which most modern cars will not, but if you have an older, very old car, it hasn't had its radiator changed in a very long time, it could have this older antifreeze in it. If it leaks all over the sidewalk or the grass or the ditch or whatever, animals will drink it because it tastes sweet. And this will accumulate in their liver and they'll die. Right? This has been known in a lot of cases where people tried to poison other animals with it. So instead, recently, we've switched over to using exclusively safer antifreezes. And it's a very simple change. You see, we just added a carbon. Right? So one more carbon makes a world of difference. This 1,2-propane diol, same thing. It's a glycol. It functions nearly equally as well as the old antifreeze. Works great. If you expose an animal to it, they drink it, it still has a slight sweet taste. And if it gets in the liver will do the same thing. This one will be turned into a carboxylic acid because it's primary. This one, however, is secondary, so the most it can turn into is a ketone. Right? So it can only be oxidized once. We'll talk about that more later. But the resulting molecule is pyruvic acid, or pyruvate, which is incredibly safe. Right? It's one of the molecules in our metabolic pathways. So we go from highly toxic to harmless. Right? Let's choose this antifreeze instead. That's the reason why we've exclusively made antifreezes no longer out of this molecule and out of this one, by one carbon difference. Okay. And one other story I want to tell you is biological antifreeze. It's used in a lot of organisms that can survive freezing. So what happens is, if you buy some ice cream and you put it in the freezer, you thaw it out, you put it back in the freezer, you thaw it out to get some more, you put it back in the freezer. That freeze-thawing cycle, or if you just leave it in the freezer, modern freezers also have a freeze-thaw cycle to prevent frost. If you ever notice in our biochem lab, if you look in the freezer, it's not one of those new frost-free freezers because we don't want those. I want it to stay frozen all the time. So there's a nice layer of snow and frost in there that we have to clean out about once every year or two. But when you freeze-thaw things like that, the liquids, the water in it, refreezes and it forms ice crystals. So you've ever done this, you've probably seen ice cream that's been thawed out and put back in the freezer too many times. The top of it's kind of crunchy because of all the ice crystals. And that doesn't taste very good. But in the case of freeze-thawing, ice crystals are bad for cells because they form very sharp icicles, microscopic size icicles, and they puncture cell membranes and cell walls. So if you could freeze an organism like a human and then thaw them back out, we would not survive that process because even if you thawed us out right away, all those little ice crystals that formed would puncture nearly every membrane in the organism and they would die. Right? But there are organisms that can survive freezing. Right? And what they do is they make this molecule called glycerin or glycerol, right? Or if you're from England, it's glycerine. Right? So there's a song about that. So another name for this is the proper name, right? It's got 1, 2, 3 carbons, so propane triol, and it's on 1, 2, 3, but we typically call it glycerol, right? And what happens is this mixes with the water in their blood and tissues, right? It's very soluble, right? Mixes with all the blood in the tissues, and when this particular animal, it's a frog that does this, and when it gets frozen solid over the winter, this glycerol interacts with the water molecules very extensively and prevents them from forming sharp crystals. So it just freezes solid. There are no crystals in it. And when you thaw them out in the spring, it takes them a few hours to get up and moving again, but no worse for the wear. They didn't lose very many cells because this survived, is prevented forming all those ice crystals. We also use this molecule to build most of the fats in our body, right? So we use this as the basis or the skeleton, and we can put lots of things on these OH groups, and it builds all the lipids in our body. Right, make up your cell membranes themselves. Okay. And then finally, let's talk about some physical properties of these alcohols. So we did this before when we discussed alkanes, right? And I gave you a general rule of thumb, and it's not perfect, but it gets better as the carbon chain gets longer, right? If I start with this propane here, right, and I add one more carbon, the boiling point increases. I said roughly 30 degrees per carbon, which is true, but on the lower end, when you have very few carbons, it's a little more drastic than that. As we increase the carbon chain, it gets closer to a 30-degree difference. So we start out with propane. Its boiling point is negative 42 Celsius. If I add one more carbon, making it butane, it's now around negative 1 degree Celsius. So it's gone up around 40 degrees. Not quite the 30 I said, but again, it gets smaller and smaller and closer to 30 as I add more. If I were to go to 5 carbons, I'd expect this to go up to somewhere around 30 or 35 degrees. If I went up to 6 carbons, I expect it to be somewhere around 60 degrees, and that's exactly what happens. So roughly 30-degree increase for every carbon. But when I add an OH group, it's quite different. So this propane, right, is much smaller than this butane, right? Butane has more carbons. It's more massive. That makes sense. This 1-propanol down here has more mass than the propane, of course, because I've added another big element like oxygen. But this 1-propanol, right, has about the same mass as this butane. And it's about 100 degrees higher in boiling point. So this OH clearly has a dramatic effect. It didn't just go up 30 or 40 degrees, it went up over 100 degrees. In fact, nearly 140. Right? So on average, if I add a carbon, you can say the boiling point is going to go up around 30 degrees. If I add an OH, it goes up about 100 degrees. That's a huge difference. And it's because of all the hydrogen bonding. So if I have this propanol, I add one OH, or so propane, and I add one OH, it goes up about 100 degrees. If I add a second OH, right, so here's our 1, 2, 3, our 1, 2 propane diol, it goes up about another 100 degrees. And if I add a third OH, right, here's our glycerol, it goes up yet another 100 degrees. So the boiling point of this is nearly 3 times higher than the boiling point of water. Right, so it's nearly 300 degrees Celsius, not 100 degrees, if it was just water. And if this had the same mass as a corresponding alkane, this would be much, much lower. It'd be far below 100 degrees. whereas this one is nearly 300 degrees. So OH groups have a huge difference on boiling point. So if I ask you to rank something by its boiling point, the first thing you should look for, even before you count carbons, is does it have OH groups? Because those will make the biggest impact. And then how many does it have? For every one, it's going to make another 100-degree impact on the boiling point. Okay? And the last physical property, other than boiling points, is are they soluble in water? Right? So most alkanes, right, all the way from methane all the way up to 30 carbon tar, right, they're not soluble in water, right, because they're nonpolar. But with this OH group present, go back a second, these have OH groups on them now. So there's some polar bonds down here, right? This carbon-oxygen bond is polar, this O and H bond is polar. This thing has a bent arrangement, not like it's shown here, but it's a bent molecular geometry. So this end is polar, but this end is not. So this end down here will not interact well with water, but the carbon on which the OH is placed will interact with water fairly well. So as long as I don't have too many carbons, this thing's going to be soluble in water. So anywhere up to about 5 carbons, 1 through 4 definitely, sometimes 5, with one OH group, monohydroxy, that means one OH group, right, alcohols, it's going to be completely soluble in water. If I go beyond 5 carbons, say 6 carbons, 7 carbons, the hydrocarbon part of the chain, the CHs on the end, get more dominating in the properties of the molecule. That one OH on the end can't do the job of keeping it soluble in water. And so these are sort of soluble in water, right? They don't dissolve very well. They don't mix with water very well. If I go above 7 carbons, 8, 9, 10, 30, 40, 50 carbons, absolutely not going to dissolve in water. It'll form 2 layers, much like the regular old hydrocarbons do. Because that part of the molecule is more dominant than that one OH on the end. How can I make it more water soluble? Add more OHs. So if you look back, this glycerol molecule, even though it only has 3 carbons, even if it only had 1 OH, would be very soluble in water. But if I made this carbon chain, say 9 carbons long, and spaced these OHs out along the chain, so 9 carbons long with 3 OHs, that would be soluble in water. I know I said above 7 it's insoluble in water, but that's with 1 OH. With 3, I'm spreading out that behavior of interacting with water, so it becomes more soluble in water. If I had those 9 carbons again, and I put those 3 OHs all in the first carbon, it still wouldn't be soluble in water, because all the effect is in one area. Right? So I need to spread the OHs around. And we'll see that when we look at a lot of our biological molecules later. Okay? We'll talk about the hydration of alkenes. We did this once before. We applied Markovnikov's rule, but it was just adding an adding an H and an OH to each side, and we reduced our double bond down to a single bond. But if you remember, we took this alkene, and when you add water, you end up with an alcohol. This is how we make them. And we'll talk about how to put those together into making alcohols next time.